Mars, the god of war and the source of man's science-fictional demise. It has fired our imagination for thousands of years. We know the dry, barren planet was once flowing with vast reservoirs of water, the sky thick and filled with clouds, and the tantalizing possibility of life. It is the only other place in our solar system that man might one day call home. We Earthlings have fired numerous probes and satellites towards the Red Planet. An invasion of sorts, not for conquest, but for knowledge. What happened to Mars? Is there or has there ever been life on the planet?
A fundamental question that needs to be answered is life as we know it on Earth, even the simplest type of microbial life, unique? If we were to go to Mars and we were to find evidence of early microbial life, or maybe even present life that somehow survived in the near surface, would it be the same as the early life that developed on Earth? That's a very fundamental question. Does life emerge generally in planets where the conditions for life are favorable, if we find out that they were favorable on Mars? Or might life take its own unique path in different environments and turn out differently?
We have bombarded Mars with satellites and landers, but there have been more failures than successes. The Soviets established 2 Mars orbiters, while NASA landed 2 Viking landers carrying complex analytical laboratories and searched for signs of microbial life. Their findings were inconclusive. Further missions to Mars still had a high mortality rate, but the successes were outstanding, with robotic probes operating for years beyond their initial missions. In fact, Mars is a planet occupied solely by robots on the surface and satellites peering down from above. All these instruments perform admirably in their specified fields of endeavor, giving us a much clearer picture of the planet and its history. The science was following the water, what happened to it, and where it is now.
Thanks to the specific instrumentation on board the mission, we are able to tell us what kind of ice did we find. And the result is that there is a mix of CO2 ice, or carbon dioxide ice, and water ice. And it's very important to characterize it, especially for the water ice or frozen water, because one of the main objectives of any mission to Mars is to trace the water on Mars in every form, liquid if possible, solid, water vapor. So it's very important to study the ice because it's one of the reservoirs of water on the planet.
The science was conclusive. There was water on Mars. There were ancient lakes and rivers, even an ocean. We needed to learn more. With the advancement of analytical technology, computer power and robotics, a new rover was constructed. Big, complex and heavy, it required a new way to land on Mars safely. Engineers came up with a system that couldn't be fully tested here on Earth. It required a lot of things to happen correctly, on time and in order. This was the Sky Crane, and the rover Curiosity was the first to try it out. A controlled re-entry with heat shield, aerobraking with a parachute, all pretty standard. Then a rocket-powered Sky Crane drops from the aeroshell and gently descends toward the surface, spooling out the rover below on cables. The rover touches down, cuts the cables, and releases the Sky Crane to fly off and crash harmlessly. The Curiosity rover has been an astounding success, traversing the terrain for over 10 years, taking samples, drilling and studying rock formations, zapping samples with a powerful laser, and photographing its progress.
Now, in the belly of that rover is an instrument called SAM. It's an instrument suite that has a couple different instruments in it that allow us to look at different types of gases. It helps us understand the chemical composition of the atmosphere and the end of minerals that might be found in the rocks and the soils on the surface. In particular, it helps us identify organic molecules that might be present.
So the sorts of evidence we're looking for, sorts of signatures of past life that we would be looking for would be signatures of microbial life. So not realistically looking for dinosaur bones and that kind of thing. If life ever existed on Mars, we expect it to have been microorganisms.
Orbiters, including Mars Odyssey and Mars Express, have been hunting down life as well from orbit.
After 10 years of mission, we have achieved a global view of Mars, and then we know at every location on the surface if you find some special minerals or not. So we have really the global view that tells us the history of Mars. Mars Express has, for the first time, detected methane, and also the concentration in the atmosphere vary from a place to another, from a season to another. And this discovery has been very debated in the scientific community because, in fact, methane should not be there because it's being destroyed in the atmosphere by the ultraviolet radiation. So if methane is there, there must be a source of methane, and for the time being, the origin of this source is largely unknown.
However, with Curiosity prowling around Gale Crater, it too detected seasonal methane.
Now, methane has been found previously in the Martian atmosphere by both Earth-based telescopes and spaceborne orbiters. But this is the first time that we've actually seen a sharp increase and decrease in the abundance of methane in the atmosphere in Gale Crater. And what this really means is that present-day Mars is an active environment.
The big question is, what is the origin of this methane now being released? The two principal areas are, first, by analogy with the Earth, it could be released and produced initially primarily by biology. This would be microbial activity acting on certain chemicals below the surface and then producing methane as a byproduct. But of course, we can't state with certitude that it is biologically produced. And so we also consider geochemical mechanisms in which carbon dioxide is actually combining with water and producing methane under very high temperatures and pressures. And that methane can then be released in the atmosphere separately.
Now, at this point, we don't have enough evidence to tell us whether or not the organics we're finding are biological or non-biological in origin. There are several viable non-biological explanations, including this organic material could have come down from space, from meteorites or comets, or organics can be formed by geological reactions in the rock itself. Now, what's exciting about this discovery is it gives us new hope in the search for chemical evidence of life. We found the organic material. Now, the next step is trying to figure out what its origin is.
Main engine start, ignition, and liftoff of the Atlas V with Maven, looking for clues about the evolution of Mars through its atmosphere.
The latest NASA orbiter mission is Maven. Launched in November 2013, it made orbit 10 months later.
Maven is the Mars Atmosphere and Volatile Evolution mission. Our goal is to study the role that loss to space has played in the history of the atmosphere. Where did the water go? Where did the CO2 go from the early planet? These are important questions to understand how Mars went from an early warm, wet environment to the cold, dry environment we see today.
There's evidence of water flowing on Mars at one point in time, perhaps even oceans on Mars. And what happened that it's so barren at this point in time? And a key part of that is the atmosphere, and it's a much thinner atmosphere than what scientists believe it was at one point in time. So the stripping away of that upper atmosphere. That's what MAVEN is going after, the climate change at Mars.
One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. The sun constantly emits high-energy photons. When these enter a planet's atmosphere, it can crash into a molecule, knocking loose an electron and turning it into an ion. When this happens in the presence of a magnetic field, the ions are captured and spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, these ions are carried away. Depending on where they form, other ions will not be carried away but will hit the top of the atmosphere. These ions crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. As this process continues over billions of years, Mars' atmosphere has disappeared, and along with it, the water. How much water has Mars lost this way?
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
Water naturally carries a heavy isotope of hydrogen, deuterium, which remains trapped in the water cycle while normal hydrogen is lost to space. Detecting the amount of deuterium enrichment tells us how much water has been lost.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
So in the ancient past, we have some indications of water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our oceans, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer.
It's fascinating that we can learn so much about 4.5 billion years ago with measurements taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
Building on this knowledge, scientists are developing the next series of robotic probes to be sent to Mars in the coming years. This time, NASA is building on its successes, utilizing hardware and systems that they know will work.
We've been to Mars before with the JPL Lockheed Martin team. We've been to the surface of Mars before successfully with Phoenix. We know how to operate the arm. The surface operations are much, much simpler than Phoenix. We're putting 2 instruments on the surface, and then we're leaving them there with no ground-in-the-loop interaction, repetitive, weekly uplink, downlink sessions. We're just made to do this mission.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core and sort of the relationship between those.
It's going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed. And what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at the basically the wobble of Mars to help understand what the core size may be in composition.
The European Space Agency is also well along with ExoMars, a rover with advanced drilling capability due to be launched by 2018. Its principal goal? To drill down deep in search of microorganisms.
What is new with ExoMars, with the rover in particular, is what we call the mobility. Mobility not only horizontal, but also vertical. And this is a peculiar thing that we have on board the ExoMars mission. So we will be able to sample material from below the surface. That is quite important to understand if there is any sign of past life activity on Mars.
We will be looking for the first time in the 3rd dimension, the 3rd dimension being depth. And we think that is where we have the highest chance of making an interesting discovery regarding the presence of organic molecules in Mars.
It's a whole planet out there with a complicated history. That history is a story that's stored in the rocks, and our job is to figure out that story and what that story of that planet tells us about this planet that we live on.
So where Curiosity takes rocks and grinds them up into powder and looks at their bulk constituents, what this mission would need to do is be able to look in a microscopic level and examine the rocks for these very tiny and detailed messages that they would be sending to us about the past life that could have lived there.
This that I'm holding up here is a classic biosignature from the Earth. It's a fossil. We're not actually expecting to see a fossil of shells or other components, but what we want to be able to see are, with this instrumentation, are the fine scale layering that one might see in a rock, in which we can see dark and light toned layers. And those dark and light toned layers are telling a story.
When will NASA send astronauts to Mars?
4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
The first test flight of the Orion crew capsule is complete. The hardware and systems are ready for mass production. The components, the engineering, the manufacturing are all underway, with NASA looking back to what worked in the past and utilizing it for the future.
Fire.
The solid rocket booster technology straight from the space shuttle has been extended and tested. NASA's new Space Launch System, or SLS, is coming closer to fruition, reusing the space shuttle's main engines as the new system's workhorses, saving billions of dollars and years in research and development. The Europeans are teaming up with NASA to provide the service model for Orion, allowing for long-duration, deep space flights. Autonomous Martian landing systems are well advanced and being tested. Software and hardware are fully integrated for both manned and unmanned Martian landings. And when they get there,
Desert RAT stands for Desert Research and Technology Studies. This is a group of engineers and scientists.
We're looking to test out new concepts, procedures, equipment like rover concepts to see how they work in the field environment.
So the team tests these technologies to make sure that in future human spaceflight missions we'll be able to do science as best as we can. That's something that NASA's never done, two human rovers at the same time. So we're really trying to develop how do you use these assets at the same time, and interesting things that you might not think about are your communications. So you potentially have 4 astronauts talking all at the same time to mission control or science communication background.
It's just like running a real mission, say, like you can think about the Apollo mission to the moon. You had the astronauts on the moon and you had the people mission control, but there was a science backroom you didn't hear about, but the astronauts were getting information from them.
Arizona has a very good climate for these types of analog studies. You have pretty much open plains and you have a lot of geological features that are analogous to places on the moon and on Mars.
long-term space voyages are being replicated on the ground and in orbit with the ISS. Surface habitats, power systems, food and oxygen supply manufacturing are also on the drawing board.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
NASA isn't the only one with its eye on this prize. ESA and now the Indian Space Research Organization have a spacecraft orbiting Mars, and they did it on their first attempt. Private enterprise is hard at work as well. Mars 500, Mars One, the Mars Society, Mars Foundation, and the Mars Initiative, to name a few. And they have volunteers lining up already for a one-way trip to Mars. It is inevitable that we will set foot on Mars in the very near future. We will stay and learn her secrets. Perhaps in the future we will be able to alter the atmospheric density through terraforming and return Mars to the world that it once was, awash with oceans and rivers, clouds and rain. Maybe some of us could call it home.